afterwards, and we'll also be sending the slides as well. These other areas, and we'll obviously be having a bigger section on solar thermal options. So our speakers today are from Ecotherm. Now, Ecotherm is an Austrian family-based business that dates back to 1880. It's one of the world's market leaders for customized water, heat, steam, and solar thermal solutions for hotels, hospitals, and industrial applications. And they now sell in over 30 countries globally. They specialize in combining all available energy sources, including gas, oil, electricity, heat, waste, and renewable energy sources to design the most energy efficient and sustainable systems. So today we'll be hearing from Anthony Castells. Anthony holds a master's degree in industrial engineering from Polytechnic University Catalonia, specialising in mechanics. And since 2014, he's been involved in R&D, engineering development of the linear Fresnel's technology that we will see today, and leading solar development, including several projects with different solar technologies in various sectors and applications. And then secondly, we will be hearing from Fabienne Eichhorn, who is the International Sales and Project Manager at Ecotherm. He's been working there for over 13 years, has a lot of knowledge over a lot of different projects. So please ask questions directly in the chat if you have anything while we have these two speakers on. Fabienne holds a degree in mechanical and economic engineering. He studied at the University of Applied Science in Wales, majoring in plant building engineering. So a little bit about industrial process heat. So industrial process heat constitute a significant 21.4% of Australia's total energy consumption, and a staggering 90% of that still comes from fossil fuels. We can see here a zero carbon industrial heat. To get to this decarbonised process, there's three main pathways. So zero carbon fuels, zero carbon heat, and zero carbon electrification. We'll be touching on a few of these, but not all of them. Obviously, there's also on the flip side of this, the waste heat that is then produced from the heat, and also then requirement for electricity on cooling. If you are interested in some of these areas that we won't be touching on today, we will be hosting future webinars on these. So please follow along or sign up to our newsletter to get notified. So in Australia, according to ARENA, 48% of total process heat consumed by industry is at 250 degrees or below. And you can see here on this graph that most of it, 46%, is natural gas, 22% still coming from black coal. To get to 2050 net zero, around 50% of total energy will still have to come from heat. And we can see the pathways here. Currently, or in 2022, we could see 40% energy from fuel, 32% from power, and 28% from heat. By the end of 2050, renewable fuels will have to be at 20%, renewable power at 60%, and renewable heat at 20%. And this is just the percentage of that will be converted to heat. And some of the different technologies that we already have developed that can help to change this over to renewable sources. Today, we only use 10% renewable heat. So there's a lot of work to do to decarbonise this area. And with that, I will let Anthony take over and present on solar Fresnels and solar thermal solutions.
So good afternoon, everyone. Thank you, Tia, for the introduction. I'm quite delighted to be able to be holding this webinar today and sharing our technologies and Ecotherm's know-how on how we support industries decarbonize, and how we've been doing that on the past decades. So I will just switch to my presentation. So when we talk about decarbonizing the industry, we like to have a look where we are starting from. What is the starting point? This slide was briefly introduced just now by Tia. So, but I wanted to have a deeper look on it. So we can see for the Australian market and the energy share in the Australian market that the industry has quite a heavy plays a heavy role on that, where we can see that 42% of the industry accounts for the total final energy consumption. And of that 42%, we can see that half of it is for process heat. This means actually that process heat by itself accounts for between 20 and 25% of Australia's final energy use. This is a similar share as we can see also, for example, here in Europe. It's quite similar. Actually, the distribution between industry, transport, and residential and commercial is similar worldwide. But I want to make special emphasis on the right part of the graph, where we can see the temperature distribution of this process heat. So we can see that up to around 50% of that process heat is in a temperature range up to 250 degrees. So 50% of the total process heat energy use is in a temperature range of up to 250 degrees. Of course, the message is more than or around 90% of that process heat comes from fossil fuels. So this is where we are starting, and this is what we are as Ecotherm we are tackling and trying to support companies to the journey to decarbonization with our innovations. So the first message is why solar. So first place, of course, it's decarbonization. So the will to reduce the carbon emissions that we are sending to the atmosphere, but not only that. So there are other advantages that go together with solar. One is, of course, the reduction of the dependency. So solar, it means that you are generating yourself part of the energy that you are consumption. So you are reducing your dependency on external suppliers of that energy. This means also reducing your dependency on fuel prices that we don't know how they might turn out in the short term, mid term, long term, and also the replacement of future conventional operation costs for heat from the existing conventional heat systems by well-known investment costs that are related to solar, and where we also know how the solar installation will behave in the full lifetime of the project. So this long-term cost consistency leads also to an estimation of the cost of the heat that we will be achieving by solar, and we can see here an estimation of this levelized cost of heat using solar for process heat, and we will see right now what that means between 4 and 6 cents of Australian dollar per kilowatt hour. So we at Ecotherm, we've been doing for many decades now conventional solar thermal installations for mainly domestic hot water generation. You can see here, this is actually a picture of one of our installations. So we have a lot of experience and we've done a lot of projects with that. This is one end of the solar thermal spectrum of technologies, flat plate collectors. On the other end of the spectrum, we can see the thermo-solar power plants, and the concept is quite different. So in these days, so the installers of these installations, they aim to make the biggest solar field possible in order to make out be able to make out the most energy as possible into the concentration point. And the ultimate goal of these kind of technologies is to make steam, run a turbine, and generate electricity. And we can see here that the operation temperatures of these technologies are quite high, around at least 500, 600 degrees. So we identified in the middle a temperature gap. So, okay, with conventional Solar thermal technologies, we can do domestic hot water up to 80, 100 degrees. The newest ones, maybe with evacuated tubes, we can go a little higher. And on the other end, we have the big thermosolar power plant. So we had a big gap in the middle where we said, okay, there is room, and actually there is quite a big demand in the form of process heat worldwide that needs this solution in solar. And this is where we started the development process of our Fresnel technology. And here we can see the different solutions that we are offering depending on the different temperature ranges that we can see on process heat. Okay, so we say it up to 250 degrees. Of course, there are processes that require higher temperatures, but we've seen that 50% of that process heat is up to 250 degrees. So we can see here for different processes like chemical industry or food and beverage industry, where we have a range up to 230 degrees. Of course, this varies. We usually see temperature ranges between 150 and 200 degrees, also in the form of steam. Pressures of 6 to 12 bar is the most common pressures that we see on the industries. So for lower temperatures, we have our line of flat plate collectors. Then also we have our line of evacuated tube collectors. But then, and especially what we're going to talk about today, is our linear Fresnel solution, a concentrating technology that allows us to concentrate the solar light into a pipe, and on that pipe be able to either generate pressurized hot water or steam. Also, in parallel to solar, we have a line of electric boilers where basically we can generate all those range of pressures and temperatures, but using electricity as the source of the boilers, or reducing or eliminating completely and in one step all the dependency on the fuel fossils and all the emissions of carbon related fuels. Also easily combinable with photovoltaic installations. Yeah, on the little note on the bottom right part of the slide that you can see is a graph on how different solar technologies behave depending on the temperatures that we are aiming to achieve. Of course, we always compare the delta T, the difference between the temperature you want to achieve and the temperature where you're starting from, or the ambient temperature. So you can see, for example, that for flat plate collectors, they are quite efficient when the different temperature is low, the delta T is low. And as higher this temperature gets, the less interesting they tend to be. This is also relating to ETC, evacuated tube collectors. And you can see how linear Fresnel collectors, they have a much more flat line. So even for higher temperatures, the efficiency of the system remains competitive, remains good. So there are different concentrating technologies. One of the also very well known is parabolic drafts. So we consider them sister technologies. We have the parabolic draft, we have the linear Fresnel technologies, and we have the let's say central receiver, or the unique heliostats that are all of them focusing the solar light into the tower. There are also the solar dishes. There are also other technologies or variations of these technologies that we could have included in this slide. But I would say these three are the most implemented technologies. In first place, so the characteristics of Fresnel is that they are composed of long and thin mirror stripes, all of them located into the same plane. So it's not like the parabola, which is just only one mirror and all of it is tilting. It's like pieces of that parabola. They are all placed together on the same plane, and all of these mirrors are pivoting together, are following the sun. On top of it, there is the receiver. There is a pipe where all the solar light is focused from down below, and where there is the heat transfer fluid flowing through. A difference, for example, between the the Fresnel and the parabola is that Fresnel has a stationary receiver. The receiver is fixed and never moves. On a parabola, for example, the mirror and the receiver and everything moves together. Why did we choose to go for Fresnel? Could be the question. In our approach, we are aiming to put as much density of mirror per gross area as we can. So we have maximized some of the characteristics of the Fresnel. For instance, we are working with extremely narrow mirror stripes. So they are around 9-10 centimeters wide, and they are flat because they are so narrow, they are flat. And we are able to put them in a very compact way, leaving only between 3 and 4 millimeters of space between the mirrors, and we are able to um, manufacture what we called the mirror module. So we have a concept where our concept is based on a prefabrication of panels, like other solar technologies, like we are inspired on PV or on flat plate collectors, where we have a unit which is completely finalized and assembled in our factory, and we can deliver that and directly have a plug and play concept. So where it's directly placed on the rooftop, and we are able to start concentrating the solar light immediately without the need of mounting the all the mirrors on its own on site on the rooftops. So we have a prefabrication concept of these mirror modules, and we can do that because we are working with these very narrow mirror stripes, which allow us to put a lot of density of mirror per gross area. So this is also quite important when we are tackling the industrial market, because we know that there is scarcity of space. So we aim at available rooftops of buildings, and they have limited areas. So with the different prefabricated panels, we are very flexible and we're very modular. We can cover very effectively a lot of that gross area with mirror. And the second big advantage why we consider Fresnel to be a perfect fit for the industry is that with our mirrors that are, I say, between 9 and 10 centimeters wide, uh, when they are completely tilted because they are following the sun and the sun is going down and they tilt completely, um, let's say the height of the module is still not higher than 20 centimeters, and everything is well covered by the frames of these prefabricated panels. This means that one of the typical problems, which is the wind resistance that these solar mirrors need to withstand, with the our approach of Fresnel, we have practically zero wind resistance because the prefabricated panels, they are located on the rooftop flat, and the mirrors are protected by them. So basically, these are the two I call them USPs that we try to maximize, and why we believe that Fresnel is the perfect solution for the industries and the characteristics that the industries have. And special mention to DNI. So there are so solar irradiation comes to Earth in the form of diffuse and direct irradiation. So diffuse is the light that is scattered by the clouds where it gets diffuse. Direct irradiation is the direct beams that come from the sun and meet um, the surface. Concentrating technologies, because they need to reflect those beams, they benefit from the DNI, whereas non-concentrating technologies like PV or flat plate collectors, they benefit from both, from the diffuse and the direct irradiation of the sun. I wanted to share the DNA map, resource map, and we can see that there are, let's say, 4 main hotspots in the world, and of course, Australia is one of it. Of course, also special mention that the areas where the highest irradiance is, maybe it's not the areas where most of the density of industry is located. But anyway, the values of irradiance that we can see on the upper and east part of Australia, they are again still extremely good, and and pretty much the best, some of the best that there are around the globe. So this is how our Fresnel solution looks like. You can see here in the picture, you can see the very narrow mirror stripes, all of them stacked together with practically no space between them. You can also see in the picture the parabola, so the form of the parabola, because all of the mirrors have a slightly different angle so that they can effectively focus the solar light into the receiver. And with this solar concentration, we are able to tackle the different demands that we find in the industry. For example, we can do steam generation, and here again a distinction, we can do direct steam generation, meaning that we directly evaporate and generate steam on the receiver throughout the solar field, and then we separate that saturated steam from the condensates, and then we deliver only the saturated steam. We can do indirect steam generation, meaning that we can have pressurized hot water or even thermal oil flowing through a primary circuit throughout the solar field, and then via one of our heat exchangers, we can generate steam and then deliver the steam on a secondary loop. We can have a generation of pressurized hot water. We can heat up thermal oil. We can couple this technology with multiple stage, or let's say two-stage absorption chillers to do high efficiency solar cooling, or we can even target district heating applications which are quite common in Central and Northern Europe. And we say, so house numbers, that the temperature range is up to 250 degrees or 25 bars. Again, most of the applications that we see are slightly below that, but we feel quite comfortable that we can tackle pretty much most of the process heat consumption out there in that kind of temperature range. So basically, most of these points I've probably already mentioned, but I wanted to show you how we build in this picture, how we build our solar fields. So you can see here in this square, you can see 2 units of our prefabricated panel. In the orange square, which we place in parallel, and in the middle of that, we build up the receiver, so that we have 2 panels in parallel, and on top of it the receiver is mounted, and here is where we flow the heat transfer fluid. We control all the mirrors within those 2 panels with only using one electric drive, which is located a little outside the solar field. And also we have a cleaning device which automatically can clean the mirror surface throughout the whole solar field. Show you a little bit more on that in a couple of slides. So the system is quite easy to install. So basically placing the prefabricated mirror modules on the final position, a little bit that there needs to be an adjustment on the height. The height is perfect, and then only the pipe needs to be mounted on top of that, and the motor needs to be coupled. The solar tracking of the mirrors is done all by our control panels. So it's based on the location and the direction of the solar field, where the motors themselves know and can calculate the exact position that they need to move to, so that they constantly follow the sun. And given that we are tackling rooftop applications, or the height, the weight of the system, the total weight of the system, once it is operating, is around 25 kilograms per square meter. We not only do we manufacture and deliver and install the concentrating technology, but also all the required components for a turnkey system. So this goes in first place from the complete primary circuit and hydraulic components that are necessary for the good operation of the system, and also, as we can see here, the control system. So all the control system, not only for the tracking of the mirrors, but also for this primary circuit, which needs to constantly be reacting to what is happening from the solar part. So the solar has a very dynamic behavior, and the primary circuit needs to react according to what is happening on the solar field. Also, there are safety requirements that we tackle using our control system. So in order to defocus the mirrors if temperatures are getting too high because there is no consumption from the part of the on the industry side. This happens already completely automatically, but also the heat up phase every morning, ramp down phase in the evening, everything is optimized so that the solar field delivers the maximum performance. So this is just a photo of our first installation. This is in our company. This is how the solar irradiation looks like when we are completely focusing all the solar light on a sunny day in Austria. You can see throughout the receiver, the lower part of the receiver, or the solar concentration. As the sun moves, everything moves. So we would see the movement of the shadows of the receiver, for instance, as they move through. You can see again here the accuracy of the parabola that we need to give to all the different mirrors so that they focus the solar light. So a quick peek on our different references. So basically the picture that we just saw, and this picture, this is our first plant. This is our demonstration plant and the plant that we started building when we did the development of this technology. It is commissioned in 2016. It is a steam generation plant, so a direct steam generation plant. So we have a fully operational steam generation plant operating since 2016. We are, of course, making use of that heat in our own factory. So, which is so on the one side we have a testing lab. On the other side, we benefit from the heat that we are generating. But I think that the most interesting references is on one part the installation that we commissioned around 1.5 years ago at a chemical company here close to Barcelona, which is a manufacturing site of the Swiss company Givaudan, which they are making flavors and fragrances. It is a steam generation plant, also direct steam generation, operating at higher values than ours. So we are connected to the 12 bar steam line of the factory and to the 20 bar steam line of the factory. Right now we are operating it at 12 bar, also because of efficiency purposes. The lower the temperature, the more efficiency it is. When we have the chance, when they have no consumption at the 12 bar line, to put the heat on the 20 bar line. So this is just a couple of additional pictures. You can see here the quality of the concentration. It is 800 square meters of mirror area in around 1,000 square meters of gross area. And this is the second plant. This is a plant that it is on the rooftop of a food company called Poda de Bo, also here close to Barcelona, where we installed between skylights, and we had to do quite some tricks there. We installed 360 square meters of solar mirrors, and in this case, it is a pressurized hot water installation. We are delivering hot water at 120, 130 degrees for both their cooking and their cleaning processes that they have. And here's a series of also small references that we did between the two um, the two projects. Here I wanted to show you how the panels look like before we transport them. So you can see here three stacks of prefabricated mirror panels ready to be installed in a factory. You can see here we have stacked up to 12 of these mirror panels, and using this stack we lift them directly either into a simple trailer for transportation or into a standard container, and this way we can very easily transport and deliver high quantities of mirror area ready to be installed and ready to use, with quite a high efficiency of transportation. Secondly, maintenance is a key aspect of concentrating technologies, because if the reflectivity of the mirrors is degraded because of soiling or dust remaining on top of the mirrors, then this has a direct impact on the efficiency of the system. So we have developed a cleaning unit, taking advantage of our prefabricated panel concept. We make use of the structure of the panel to make this platform that you can see on the picture roll throughout the full solar field in the direction of the mirrors, and of course achieving a quite optimum, let's say, cleaning costs and cleaning optimum efficiency. So we have no manpower related to that because it is fully autonomous. It has an included charging station. So when the cleaning is completed, the robot comes back to this position and it connects here, and it will charge again the batteries for the motors for the movement of the robot, but also it will charge automatically the water tank that needs for spraying the water on top of the receivers. And I will try to show a video, which I hope it works, where you can see how this robot is moving. You can see there are no cables, no hoses attached, because everything is fully mounted on top of it. And as it moves, it sprays, not sure if it's going to be, you can see here, it sprays on top of each mirror water with a little bit of pressurized water, so that the dust or the particles that are staying on top of the mirrors, they get removed. The frequency of the cleaning processes, the intensity or the pressure that we want to apply to that, it depends a lot on the geography. So it depends on the characteristics of each location, what kind of dirt we have there. It's not the same having the installation in the middle of a forest or having the installation in the middle of a big industrial area, where the kind of pollution that we have over there is different. So we are able to adapt this cleaning solution depending on the requirements. So I mentioned earlier that we offer the complete solution, not only the solar fields, but also everything that has to do with turnkey installation and the primary circuit. So we have a solution for steam generation, which is composed of the steam drum. So basically, we have the solar field, and on that solar field, we are evaporating part of the water that is flowing through it. We aim to the output of the solar field have a mixture of steam and hot water, not evaporate completely, and in order to avoid superheated steam. So we always want to have a mixture of saturated steam and water at saturation temperature going out of the solar field and entering the steam drum. And the steam drum, what happens inside it is it separates. So basically steam goes up, and the water at saturation temperature stays below and will get recirculated. And when the pressure inside this tank, meaning that the pressure of the steam is the right one or is the one according to the set point needed by the industrial process, we will start delivering automatically steam throughout this pressure control unit. And this pressure control unit is actually essential for this kind of installations because the integration of the solar steam generation plant into the existing system, and by existing system, I would say there is a conventional boiler on the factory, the integration is in parallel. So you have the boiler running, and when there is solar steam available, the solar steam will reduce the load of the boiler and thus providing savings and providing a reduction of the carbon emissions. When the solar steam is no longer available because it's evening and the sun is going down, or because there is suddenly a cloud covering the sun and there is a abrupt disruption of the solar generation, the combination of the steam drum and the pressure control unit gives enough time to the system to compensate, so to smoothly change the delivery of steam coming from the solar field and starting giving the needed steam from the boiler system. So this is what happens between the steam drum and the pressure control unit. And basically, there is a regulated valve which opens and closes depending on the pressure that we are having inside the steam drum and the energy that we are generating on the solar field. So depending on what is happening on the, let's say, dynamic behavior of the solar field, we will deliver more or less steam, more or less kilograms per hour of steam, but making sure that the pressure that it is entering the steam header is always the pressure that it has to be in order to avoid any disruption in the process lines of the factory. This is how a steam drum in real life looks like. We also prefabricate and pre-assemble and try to give as much as a compact solution as possible. So we deliver the designed tank with all the hydraulic components already mounted on it, already pre-wired, all the instrumentation, so that it is as easy and quickly as possible to do on site, and also reducing risks. I will, this case, for hot water applications, it's quite quick because we would just work with a heat exchanger. So we have one phase on the primary circuit. So in order to deliver the heat to the secondary circuit, we have a heat exchanger. And finally, just two messages regarding where can we locate the Fresnel installation and actually solar thermal when compared to other solar technologies. And basically, I'm going to, I mean PV, which is like the main solar technology, which is now the mainstream solar technology, which is now being installed vastly. So basically, of course, you cannot compare PV with solar thermal because one is generating electricity and the other one is generating heat. But I would say both technologies aim to be installed on the rooftops, for example, of industries. Of course, PV is a good technology. It's a mature technology which is worldwide being installed and tested and achieving every time lower and lower and lower costs. Good advantage of PV is that you can either consume the electricity, or if you have no consumption at the point, you can also feed the electricity into the grid, and depending on the countries, get a better or a worse rate for that. Of course, one big discussion nowadays, which we're not going to enter, is storage batteries. And the good thing is also that they are combined. PV is generating electricity, which is combinable, for example, with our electric boilers. Compared to that, solar thermal is generating heat, but it has a yearly generation of energy. So if we compare the electricity generated in kilowatt hours and the heat generated in kilowatt hours, solar thermal generates around three, depends on the location on the world, but around 3 times more than the same installation, the same gross area of PV would generate. So it's around 3 times more. Some places would be 2 times more. Some places would be 4 times more. The specific, we could have a look at the specifics and in Australia. Of course, the capex, the initial investment costs, are also greatly higher because the cost of the PVs are reduced, are lower and lower. So we have an installation that is yearly going to generate 3 times more, but that the initial investments are going to be 3 times higher as well, more or less. It's a rule of thumb. It has also obstacles. It's that, for example, the heat that you are generating on a solar thermal technology needs to be either consumed or dissipated, or in the case of concentrating technologies, not generated, because you can defocus automatically, as I mentioned earlier. Also for higher temperatures, like the ones we can find in process heat application, like steam at 10 bars, 15 bars, storage is an issue. But the good part is that it tackles process heat directly without needing the conversion of a boiler additionally. So basically, I would say PV investments have lower payback periods, and it is a lower risk investment. But looking at other parameters of the evaluation of that investment, solar thermal have higher payback periods, but provide a much higher net present value and internal rate of return when you look at the full lifetime of the project. So overall, it can be, if you take into consideration not only how quickly will I get my investment back, but in the 20 years or 25 years lifetime of the project, how much I will get from all of it. Solar thermal installations provide much more attractive and competitive solar solutions. And actually, given the higher efficiency, yearly savings that can be achieved in the form of heat, also a higher degree of decarbonization can be achieved with solar thermal installations. And lastly, I just had a look at the costs, for example, of natural gas. This is the SEAR, so costs of natural gas in Australia. And we can see here you are 11 Australian dollars per gigajoule, which is around 4 cents per kilowatt hour, considering that there is a boiler efficiency, you need some conversion, around 4.5 cents per hour per kilowatt hour. If you remember on my initial slides, the cost of the heat, the levelized cost of heat for a solar thermal installation, it's around 4 to 6 cents per kilowatt hour. But those costs, you can know that they will be stable, so that throughout all the 20-25 years of lifetime of the project, the costs will remain stable. Whereas with fossil fuels, we are all most welcome to speculate what will happen in the next 20-25 years, also related to carbon emissions and carbon taxes. Also, I wanted to include here a quick comparison to green hydrogen, where, if I'm not mistaken, those are the values for Australia, and we come at a price of heat of 24 cents per kilowatt hour. So solar thermal can be much more of our, can have a substantial role in the decarbonization of the Australian industry also today, because it's a mature technology. Yeah. So that was it from my side. So now I will, thank you very much. Now I will switch presentation.
Anthony, do you mind answering some of the questions that are in the chat? Is that okay? There's one from Bodhi, which says here, practically there are industry parks across the industrial area. How do we get thermal energy via these methods, which may require a large land area into process heat within these industrial parks? Is it a requirement that we will have to transport heat across large distances like we do gas electricity, or are we able to integrate those renewable heat systems into industrial areas, even brownfields?
So, of course, it depends on what it is meant by large area or land area. So we can easily install a steam generation plant in a factory which has a 1,000, 2,000 square meters of roof available. Um, so we think that decentralized generation of heat for the different industries, if they have enough rooftop available, is possible. We have I didn't mention that, but we have a tool. Just jump one slide back. We have a tool where which is basically allows us to, based on a location, connect to the solar data bank, where we can simulate for a specific process, meaning giving the desired steam pressure to be generated and the available rooftop area that we have on that location. It will give us what can a solar system for that area generate. So how much is the, I don't know, the maximum output, what will be the peak in tons per hour of steam, and what will be the yearly output that will be generated throughout the sunny hours of the year. And it is quite an easy tool to use. So I mean, when we are talking about industrial parks, of course, centralized generation is possible, and then you would have to have a larger pipeline. But I think that what we want to convey is that we can decentralize this generation of heat with this very modular and flexible technology. Needs to be looked at the process requirements, the steam demand or the yearly heat demand that everyone has in their industries or in their industrial parks, and see how much of that can be effectively converted to solar with the available area. I hope I was able to respond that question. If not, I'm happy to. You have my contact data, and I'm more than happy to enter a discussion on that. And I will.
We have two more questions, but we might jump to Fabian, and then we'll answer the other two
Or
at the end.
I will try to answer also on the text, if that's okay. In the meantime, so thank you, and switch to Fabian.
Okay, thank you, Anthony. Let's switch over to my part of the presentation about power to heat electric boilers. So very warm welcome also from my side. We are talking here about our power to heat boilers. If you do not know power to heat, just a quick overview what this means. So a very very preliminary. Load profile of the electrical energy on the grid is visualized here over 24 hours, starting from 0 to 24 hours during the day. And this example is compared with a solar PV system. So we all know renewable energy sources such as solar PV systems. They are producing electrical energy once the sun is shining. So during the day when the sun rises, the produced energy is getting more and more. And when in the evening, it will be less again. The energy requirement on the grid, of course, it's fluctuating through the whole day. This is like this profile here. So it gets more in the morning, it drops like at noontime, and it rises in the afternoon due to the industry, and it drops in the evening and it goes back on due to like lights and everything what we need. What we can do now here with the green area is the green area would be then covered by solar PV systems. So solar PV during the day they are producing electricity, and those energy we can then cover on the electrical grid by solar PV. The critical thing is now the red area here, which is not the red area, which is not are covered by the grid, or is not demanded by the grid. So this is actually like free available energy on the grid. The electrical grid is a very sensitive thing. So all the electrical energy available on the electrical grid has to be consumed. Otherwise, the electrical grid will get unstable. So with solar PV, or let's say wind energy, or any renewable energies, we only can produce energy when the sun is shining or the wind is there. So, and when the electricity is produced, we also have to consume the energy, and that's the the basic idea of power to heat. Because nowadays, okay, battery technology is not that far that we can like immediately store big amounts of electrical energy in batteries and use it on a later stage. In addition to that, big battery solutions are also not very sustainable. So what we can do is we can use this surplus of electrical energy on the grid and convert it in our electrical boilers to thermal energy. Thermal energy, it's very easy like to immediately use in district heating grids or in the industry for any process heat. So this is the basic idea then of the power to heat solution. So we use the surplus of electrical energy on the grid produced by renewable energy sources and feed it directly either into our electrical hot water boilers or electrical steam boilers, and therefore transfer the electrical energy to thermal energy and make use out of this thermal energy on a later stage. So what Ecotherm is offering here in this power to heat solutions, we are offering complete turnkey packages in electrical hot water or electrical steam boilers, which can then utilize either the free electrical energy on the grid to produce any heat. So let's jump right into our electrical steam boiler systems. What we usually do here is we make them so-called skid mounted. First thing what we're doing, we are producing so-called metal frames where we place all our components onto the skid, such as the electrical steam boiler with the heating flange, the master control panel, and all the auxiliary items like the feed water tank. We do all the piping, of course, wiring, pre-testing. Everything is pre-mounted, pre-wired, and tested here in our factory. And for transportation, we just divide those skids so we can fit it into trucks and containers and ship it to site. So one big advantage for our customers is then they have to assemble on site only like 4 to 5 pieces and put them together. They have a ready to run system without any big efforts on site for installation. The range for the electric steam boilers goes up to like 10 ton per single boiler. All our boilers are operating on low voltage, either 400 or 690 volts. And the arrangement, there can be 2 boilers, duty standby, 1 boiler only, with 2 feed water tanks, 1 common feed water tank. So it's very flexible, and all those products are tailor-made according to project requirements. Electric hot water boilers is also a turnkey package unit, which is completely skid mounted. We are using either those horizontal orientations or the vertical orientations, depending on site conditions, space availability, and size of the electrical boilers. The range goes up to 10 megawatt, even more in cascades. We can put more units side by side. And one of our USPs in the electrical hot water boilers is that we are using so-called individual heating elements, which in a range of like 18 to 15 kilowatt. So we have a very big redundancy. If one of these heating elements is failing, still like 95% or so of the total capacity of the boiler can still be operating. The complete system is, of course, also pre-mounted and pre-wired, so the dimensions are exactly measured, so we can fit it in trucks or containers and bring it to site in one piece. So our clients just have to connect water, inlet, outlet, and the electricity, and they have a system ready to run. What we can also do, what we've done in a just recent project, if our clients, they do not have any space availability in their boiler rooms, we can also containerize systems. We can mount all our electrical boilers inside containers and put them like next to the site of our client, in order to save them space inside the boiler room, or just like extending their boiler room like this. This is a project we've done for Hungary, for an industrial plant, where we mounted everything, 2 units of 1.5 ton steam boiler, and the feed water tank on top, everything in 3 20-foot containers. Also, the installation on site is very straightforward, very easy and very fast. So within, from delivery to startup, it was only like 1.5 week, where we supplied this unit and they installed everything, and we came for startup and commissioning for the whole system. So what Ecotherm is also offering nowadays is our so-called virtual reality, especially for the electric steam boiler plants. We can offer a virtual reality, so our clients, they can go through their system virtually. It's also possible to connect this with live data, so our clients can go through their plant virtually with this VR glasses and check temperatures, pressures, any conditions of the plant. This is very important also for like operator trainings or troubleshootings, when we have to assist our clients. This virtual reality is also attached to our so-called spare part shop. So if our client is in the virtual reality and wants to replace any part, he can have then directly access to our spare part shop. He has access to detailed data sheets of the unit, and he can also see the like mounting instructions in small videos. So this is very important, because not every time that we are very worldwide acting company, and our staff do not have to travel for each and every thing on site, so we can assist from here from Austria directly our clients. So I want to show you a few of our top references of the power to heat technology, what we've done so far. So we've, especially like in the last 2 years, there were a lot of projects in Europe. Electrical water heating, of course, is quite common in our export markets, like the Arabic countries, over the past 22 years, 25 years. But especially in the last 2 years, we had very good projects here in Europe, especially in Hungary, where we supplied to district heating to a private company. They are just installing the electrical boilers in total 6 megawatt there, and they are taking the excess electric energy from the grid, transferred to thermal energy in our electric hot water boilers, and this hot water they are producing in the boilers, they are giving it to the district heating network, to the district heating grid. So they get some good money from the electrical grid operator to utilize the excess electric energy from the grid, transfer it to thermal energy, and they get money from the district heating network, because they are supplying energy there. This was the containerized system for an aluminum factory also in Hungary. Actually, the picture here you can see, this is in our factory where we did the complete pre-mounting of the whole project. Everything after this picture was then dismantled into these 3 containers, was shipped to site and reassembled on site. Very fast track project, of course. In terms of food and beverage, one of our most prestigious project was for a big food and beverage company in the Netherlands. We're not allowed to tell the name, but they are producing some very sweet black soft drink. Actually, this unit, this electric boilers are electric clean steam boilers, since in the food and beverage industry also clean steam is required. Clean steam is always then necessary when the steam is getting directly in contact with any food product, for example, for sterilization process. So the complete unit is then made out of stainless steel. It was also completely skid mounted, 2 units of 2-ton boilers. And also very interesting in this project, the project was done completely virtually. So our client never visited us. The project was awarded during the COVID pandemic, during the lockdown. So we were not able to travel really. And so the client never visited us. All the factory acceptance tests and everything was done virtually. So we also gave them the virtual reality and for operator training and so on. Also in the hotel sector, electric boilers are used. For example, we equipped the Sheraton hotels in Porto and Lisbon with 1 megawatt electric hot water boilers each. They are using this for hot water generation and space heating. So this was my very short presentation about power to heat electrical boilers. If you have any questions, then please feel free and put them in the chat or contact us directly. Power to heat, in our opinion, is a very it's a topic of today. Let's say it like this, because renewable energy sources such as solar PV and wind energy and so on, they are continuously extended. But we also have to think about the electricity which is on the grid, how to utilize it. So thank you from my side. If there is any question, please feel free and go to the chat.
Thank you, Fabian. I think we have one more for Anthony, but since we are over time, we may have to finish there. But if anyone does have any questions that weren't answered today, you can email either Ecotherm or Enaxiom, which is info@enaxiom.com. And thank you very much.